All right, ladies and gentlemen, let's get started. All right. So there are three things that I want to bring to your attention. Okay. The three topics. Well, first of all, the first two topics aren't really much anything beyond putting a definition to some information, and then the last thing is quote unquote new material, but we've been doing it already. So I want to talk about what it means to be mutually exclusive. Versus independent. And then later on, we're going to talk about Bayes' theorem. Versus. I think it's with an apostrophe or not. No. Bayes was his last. Okay, Bayes' theorem very much relates all the stuff that we've been talking about. If you know how to do your tree diagrams, you're going to be generally okay. All right. If you remember that, ultimately it all kind of comes down to the idea of the probability of success over all of the probabilities. Okay. So, but let's talk about mutually exclusive for a moment. All right, so here's some things to remember about mutually exclusive. Mutual exclusiveness means that if something happens, then the other, if two events, A and B, if one of them stops the other from happening, then you're mutually exclusive. Okay. For an example would be flipping a coin. If you land a head, it cannot also be tails. It's one or the other. You are either in the group of this or you're in the group of that. There is no such thing way in between. Okay. Okay. An example of something that is not mutually exclusive would be grabbing a deck of cards and pulling out a red card. Okay. Pulling out a red card or pulling out a king. Okay, because in that situation, pulling out a king limits your odds of being red. Okay, there's an overlap between the two. There's the scenario where you could be both red and a king. So that's a situation where it's not mutually exclusive. Okay, so for example, if I said, what are the odds of you getting frostbite tomorrow? Well, that is kind of based upon the weather. So, what are the odds of it being cold, and what are the odds of you getting frostbite? Well, if the odds of you getting frostbite and being cold, and it's cold outside, those two are definitely related to each other. Okay. Granted, you could theoretically get frostbite, and it would not be cold outside. You might, pour liquid nitrogen on your hand, and now you've got frostbite. Okay, wow, that was just a little bit graphic. Now, so this is not, so in a sense, mathematically, what we're talking about is that the intersection is zero. If I said, here's a game, if you pull out a red card, you win. If you pull out a king, you win. Well, pulling out a victory in one results in the changes of victory in the other scenario. So if for example, again, let's take something that's not mutually exclusive, would be the odds of, let's do a lie detector test. Okay. Well, the odds of you passing a lie detector test and the odds of you lying are related to each other. Okay, so you could pass a lie detector test and be just lying all day long. It's a bad test. It didn't work, right? Or you could pass a lie detector test because you really were telling the truth. You could fail a lie detector test and be telling the truth. And you could fail a lie detector test and be lying all day long. So those two scenarios, are you lying or not? What are the odds of you lying? Or the person that you're administering the test to, what are the odds of them lying? And the odds of getting a positive or negative result. Those things are related to each other. Okay. Mathematically speaking, it's saying that the intersection of the two, are you lying and are you passing, are non-zero. The intersection does contain those different scenarios. So the intersection is, so if you are mutually exclusive, the intersection is zero. They are disjoint sets on a Venn diagram scenario. Okay. But mathematically, if you are mutually exclusive, you can say two events, A and B, the intersection is zero. If that's the case, that means that the union of the two probabilities would be what? I mean, if I throw a dart at that Venn diagram, what are the odds of me landing in one of the circles? Yeah, the probability of A plus the probability of B. If you're not mutually exclusive, meaning that there is an overlap, then you have to subtract that overlap. And we saw that before. Okay? We've done that 100 times. All right. Also, if the probability of A given B, right? The probability of A given B, we've done this before. Actually, we had this question last time. Well, that would be the probability of the intersection all over the probability of B, which is 0 all over the probability of B, or 0. Yeah, I'm talking about disjoint sets, mutual exclusiveness. Two events that have nothing to do with each other. Okay? So, and we can also say this is an interesting result. Probability of A given not B. Now let's look at that. The probability of A intersect not B all over the probability of not B. Well, first of all, what is the probability of not B? Well, if it's not B, and there's nothing related to A involved, not B would be, rather, oh, darn it. Not B would be all of this. Right? So how would I write that mathematically? Another way to write that would be what? 1 minus B. All right. And now, the intersect of A and not B. Well, A is all of this. So what's the overlap of the red and the blue? The red and the green? A. Okay, so that's just a mathematical way of expressing what mutual exclusivity is. Okay? So far we've been dealing primarily with mutually non-exclusive, okay, or mutually inclusive sets, okay, because those are more interesting. Okay. All right. Does this make sense? Are we feeling all right with it? Okay. We were talking about these before, where, you know, I think a long time ago we did one example. I want to say like one of the first days that we did probabilities. We did a mutually exclusive example. All right, independent. Independent. I always misspell that word. You ever have words that you always misspell? No matter how many times you correct yourself, you never get it right?
You use the wrong.
I'm sure. Yeah, it's not it's, right. All right. Moving on. All right, independent events are events that do not affect each other at all, in the sense that if I flip a coin twice, getting a heads or getting a tails on the first roll, the first flip, doesn't change the odds of the second flip. Okay? Yes, one stops the other from happening. You can't be doing both at the same time. So we've seen these before. First of all, this is a criteria of binomial distributions. You can't have events affecting each other. All right, you can't use the binomial theorem on non-independent events. And we've done these before, and these are the formulas that we've already seen. Well, the probability of event A and event B happening, we've seen these when we first did our line diagrams, right? You would have to first pass A and then pass B. So it's the probability of A times the probability of B. The odds of me rolling a coin, or rolling a die and getting a 6, and throwing a dart at a dartboard and getting a 6 are not at all related to one another. But if, in order for both of them to happen, it would be 1 out of 6 for the dart. 1 out of 6 for the die, and whatever the ratio of the areas would be on the dartboard. Okay, something like that. A union B, we've seen this before. Again, probability of A plus the probability of B minus the probability of the intersection. Okay, that one should be buried in your brains by now. All right. Okay. Also, well, let's take pulling a card out of a deck and rolling a die. One doesn't have anything to do with the other. What is the probability that I will pull an ace out of a deck if I rolled a 3 on the die? It doesn't have anything to do with each other, right? So the probability of A happening, given that B already did, okay, like, or pulling a 6 out of a deck of cards and rolling a 6 on a die. Well, if I've already rolled the 6 on the die, and now I say to myself, what are my odds of pulling a 6 out of the deck? What is that? It's still the same. Here, okay, well, I'm going to roll the die and then I'm going to pull a 6 out of the deck. Well, look, oh darn it, man, I rolled a 4. What are my odds of pulling the 6 now? Still the same. Okay, so independence and exclusivity are different. Okay? One talks about one thing, one talks about another. Okay? But one easy way to tell if something is exclusive or independent is to use this guy. Because if you look at that one for exclusivity, it was a different formula. So if I gave you a question like I will later on today, that says to you, all right, here's some information about two events. Are they exclusive? Are they independent? You would use those formulas to confirm or deny exclusivity or independence. Well, it's either this will be true or not, and the other one will either be true or not. Okay, this is one way that you can tell. Okay, but obviously because of these two formulas, you can't be both exclusive and independent at the same time. All right? If you're one, then you're not the other. You're either non-overlapping or you're overlapping. One or the other. You can't be both. Okay. In fact, mutual, now that's kind of interesting. Mutual exclusivity excludes independence, because if you are mutually exclusive, then you are not independent. But mutual exclusivity means that if one event happens, the other one doesn't, which is kind of like a self-definition in a weird way. Neat. All right, moving on. Bayes' theorem. I'm going to do it again. Bayes' theorem. Bayes' theorem is a rather simple explanation. Where did I write it? I had it written down. Like just... All right. Up, I'm upside down. I knew I was going to write it upside down too. Sorry, this is why we have erasers. Oh, tell me I wrote it wrong again. Hold on. Different books, different definitions. You'll live. B given A. Yeah, right. Now I'm right. Now I feel better. Wow. That was just no fun. I know. I erased it and then I looked back and I did it again. All right, so I was right the first time. Another way to write this, which I think is a little bit more elegant looking. And this way, it's a little bit easier to remember. AB, AB, BA. Okay. So this thing is useful when you know some, like A given B, but you're looking for B given A. Okay. So let's do an example. All right. Where is the one I wanted? Okay, by the way, I will say very often that's quite often the goal of the problem, is to find that denominator. These kinds of problems are these kinds of problems are oftentimes false positives, false negatives. Okay. Other times you're looking for the number in a population given some other information. But false negatives and false positives are kind of lend themselves to this kind of a problem. All right. So let's do this. All right. Mike and Belinda. So we have M and B are riding their bikes. Are cyclists. So here we go. I'm just going to read this off to you, guys. All right. Mike and Belinda are both keen cyclists and want to see who is the best cyclist. They do this by competing in a series of independent races and decide that the best cyclist will be the one to win 3 races. These races only have the 2 of them as contestants. However, the probability of either of them winning a race is dependent upon the weather. In the rain, the probability that Mike will win is 0.8. But when it's dry, the probability that Mike will win is 0.3. In every race, the weather is either defined as rainy or dry. Okay, there's no in between. The probability that on the day of the race the weather is rainy is 0.3. Okay. So do we all understand what's happening? These are tree problems. Yes, very, very often these are tree problems. Okay. Find the probability that Mike wins the first race. So wait. Yeah, it's the first race. So first race, second race, third race. We haven't discussed any of the subsequent races. Okay, so the first decision in our decision tree is what? Whether it's rainy or whether it's dry. So rainy and not rainy. Okay. Probability of rain is 0.3. Probability of not rain is 0.7. Now it's either going to be Mike or Belinda. Or shall we just say Mike and not Mike? Sorry, Belinda, you've been relegated to being a not. All right. It's either Mike or that other one, right? That's not very nice, but when you're dealing with a binary situation, it's either one or the other, and our contest is framed in Mike's favor. So the odds of this are rainy if it's Mike is 0.8, rainy if it's not Mike is 0.2. Not rainy, Mike is 0.3, rainy and not Mike, not rainy and not Mike is 0.7. Okay? Cool? All right, so now the question is, find the probability that Mike wins the first race. Well, there are 2 different avenues for that to happen, right? Here Mike wins, here Mike wins. Okay? So that by itself gives us this path and that path. So the probability is 0.45. We good? Oh, are we done already? There we go. All right, we'll pick this up next class. this episode of the Ronco Show just didn't happen.